Okay, so thank you very much. And so I'd like to, okay, so the previous speaker explains the experimental side of the Muon g-2. So now I'm going to explain the theory side. And so this talk is composed by the two topics. The first one is the focus on the standard model prediction, the recent progress, and there is an interesting issue or some important issue. So I will explain the standard model part. And the second part is a new physics interpretation. And we particularly focus on SUSY interpretation. Okay, so the first part is already explained by the previous speaker, so I don't have to repeat. So our target is here, L is a lepton, so A mu equal G mu minus 2 over 2. This is today's target. And so the experimental status is also mentioned by the previous speaker. So now we have 4.2 sigma deviation. And so the first part of this talk is this standard model prediction. So this standard model prediction, recently, it's almost 2 years ago, 1.5 years ago, the white paper was published, which is a new consensus, the current consensus of the standard model prediction. The standard model contribution is composed by the 4 categories. First one is a QED, and second one is the electrolytic. And also there are 2 hadronic contribution. The first one is a hadronic vacuum polarization. The leading diagram is here. And the second one is a hadronic light by light contribution, which is given by this diagram. And as you see, the largest uncertainty comes from the hadronic vacuum polarization. And recently, there is the one new issue has been raised by the new lattice result. So I'm going to explain this new lattice result. So before explaining the lattice contribution, let me first explain how the hadronic vacuum polarization has been determined, especially in white paper. In the white paper, the hadronic vacuum polarization contribution has been determined by using the experimental data of the hadronic cross-section. Actually, this is a diagram of the hadronic vacuum polarization, and this is unknown. We cannot calculate this part by hand. So but by using the gauge symmetry, analyticity, and unitarity, this unknown part can be related to the experimental data of the E plus E minus 2 hadron here. Actually, so in this traditional way, the traditional method, which is often called R ratio method, the hadronic vacuum polarization contribution is written right here. K is a known function, is an analytic function and known function. And R is a so-called R ratio, which is proportional to the experimental data cross-section of the E plus E minus 2 hadron. So once we measure the E plus E minus 2 hadron cross-section, then we can determine the hadronic vacuum polarization. So this is a traditional way. But lattice can also calculate this hadronic part. Actually, the hadronic vacuum polarization contribution can also be written right here. This is a weight function, which is again the known function, and this C is calculated by lattice. C is a correlation function of the clock current, and this is a hadronic part. This includes the hadronic part, but you can calculate this contribution by using a lattice. And very recently, okay, so 2 years ago, the BMW collaboration has published new result. The result is here, and our ratio result was here. As you can see, okay, so let me explain this blue band. The blue band is determined by the Fermi-Lab. Okay, so this was Brookhaven, but anyway, so this is consistent with the Fermi-Lab result. So this BMW result is consistent with the experimental result, Fermi of G minus result. And instead, this lattice result is deviated from the R ratio result by almost 2.1 sigma level. So this tension has not been solved yet, unfortunately. And as for the lattice part, so the paper has already published and accepted in the article, but anyway, so there are still many discussions about this BMW result, because the lattice calculation is completely non-trivial. For example, the extrapolation to the continuum limit was so the scale determination and etc. is not, they are completely non-trivial. So there are still discussions. And so we have to wait for the independent lattice computation with comparable pressure. So it's not conclusive yet. So as for the experimental data, some groups analyze the electric precision observable, because the experimental data also, these observables are also sensitive to the experimental data. So this is a trial function, trial cross section. So sigma 0 is this is the original one. The R ratio, this is determines the R ratio data, and hypothetically, this cross section is magnified by multiply the 1 plus epsilon. So epsilon is a positive number, positive parameter, and the position of the energy is S0 plus minus delta over 2 is magnified. And this epsilon is chosen to account for the difference of the muon G minus 2. I mean that to account for the lattice result, say, for instance. So then we can estimate the electric observable. This is a plot of the Higgs boson mass versus S0. S0 is the position of the deformation. And this dashed line is the experimental result of the Higgs mass. So this includes the uncertainty of the Higgs boson mass. And this green band corresponds to the epsilon equals 0. I mean that this is the original one. And if we switch on the epsilon to be non-zero, then the prediction becomes right here. This orange band and the pink band. Pink band correspond to 2 sigma, and sorry, 95% level. So as you can see, if we include epsilon, then the Higgs boson mass, the theory prediction of Higgs boson mass deviated away from the experimental result. So from this, we can say that any deviation from the R ratio data is disfavored above if the deviation happens in the larger than 1 GB. So in order to explain the electric precision data and the muon G minus difference, we have to include the enhancement in the region smaller than 1 GB. But the enhancement, the size of epsilon is much, much larger than the experimental accuracy of the R ratio data. So if such deviation happen in the experimental data, then we have to check such a deficit by future experiments, such as Bell 2 experiment, BESS3 or CMD3, and also this can independently the traditional way of the hadron vacuum polarization contribution can also be tested by using the Muon E experiment. So this is a status. This is a Fermi of muon G minus experiment, which is deviated from the standard model prediction, which is determined by the R ratio data by 4.2 sigma level. But if we adapt the BMW lattice result for the hadronic vacuum polarization, then there is no tension between the Fermi level muon G-2 result and the standard model prediction. But instead, there is a tension between the R ratio result and the BMW result by 2.1 sigma level. So there exists the tensions, and we haven't solved these tensions yet. So this is the status. And the red characters are the future prospect. The Fermi level experiment is ongoing, and JPAC is still, it's not planned, and the construction is ongoing. And as for the R ratio data, the data will be checked by the BEL2 experiment, BES3 experiment, CMD3 experiments. And as for the lattice result, there are independent analysis ongoing, so we can check. So anyway, in the near future, we can check these tensions. So this is the status. Okay, so let me go to the second part, the new physics interpretation. So the standard model value based on the white paper is deviated from the Fermi level, the Fermi level experimental data, BNL plus Fermi level data by 4.2 sigma level. And this is about 10 to minus 9, 10 to minus 9, over the 10 to minus 9, which is comparable. Actually, it is larger than the electric contribution. The electric contribution is about 50.4 times 10 to minus 10. So the current deviation is larger than the electric contribution. So if this deviation is indeed a signal of new physics, we naively expect the new physics exists in electric scale. But as you know, we haven't observed such particle. No new particle has been observed in electric scale. So in order to explain the deviation by using new physics, we have to consider some mechanism to enhance the contribution to the muon G minus. So there are two contributions, there are two possibilities, light particle as an enhancement. So the new physics contribution is naively represented right here. This is a one loop contribution, so there is a one loop factor and proportional to coupling squared, and the mass is scaled by the mass ratio squared. And depending on the model, there is an enhancement factor. So in order to explain the current deviation, one of the way to avoid the experimental constraint, one of the simple ways is to consider the tiny interaction. Then G nu is tiny. So we have to consider small m nu, I mean, that's a light particle scenario. So such light particle scenario, there are several light particle scenarios, such as a scalar extension model. So Twixt-like model, for instance, or action-like particle model. The vector extension model, including the U1 mu minus tau is one of the famous extension of this candidate. And another scenario is a heavy particle. So if we consider heavy particle, so new physics in high energy scale, then we can avoid the experimental constraint. And instead, so since this M is large, we have to consider some enhancement mechanism. I mean, just the large G nu or X enhancement is necessary. Then SUSY is one of the most famous example. And Repto-Kuoka vector-like fermion can also explain the muon G minus 2 anomaly. And also there are many works in the integration with the B anomaly, dark matter, etc. But anyway, so today we focus on the SUSY. This is the essence of the SUSY interpretation. The SUSY contribution, there are two types of SUSY contribution. They both include the muon or muon, muons neutrino and muon, muons neutrino and muon particles, and the Chajino diagram includes, this diagram includes a Chajino, and this diagram includes a neutralino. So they are often called the electroweak. But anyway, so these diagrams are dominant contribution to the muon G-2, and this contribution is enhanced, is proportional to tangent beta. So as you know, tangent beta is a ratio of the Higgs boson mass, Higgs boson vacuum excitation values. And one of the important feature of the SUSY contribution is that the muon interaction with the Higgs, which is given by the supersymmetric version of the muon Yukawa coupling, which is roughly given by the standard model Yukawa coupling times tangent beta. So this is the reason why the tangent beta appears here. And this tangent beta is over order 10. So because of this enhancement of the chirality flip, the SUSY contribution is naturally enhanced. So there are three types of the SUSY contribution. The first one is a light Uino-Higgs muon neutrino contribution. And the second one is a light B-Higgs muon contribution. And the third one is a pure B-muon contribution. So let me first explain this light Uino-Higgs scenario, because this is usually largest contribution to the muon G- in many scenarios. So in the light Uino-Higgs scenario, the light particle as a left-handed muon, the Uino and Higgs, and also we consider the B as a light superparticle. And tangent beta is over order 10. Actually, in this plot, the tangent beta is taken to be 40. And so this is a plot of the muon G-2 region, where the region where the muon G-2 is explained at the 1 sigma level and 2 sigma level. And as you can see, the muon or Chajino is in the mass range of 100 to 1 TeV. So this is actually the target of the LHC. So the LHC search is categorized by the mass, they categorize into two, so they classified into two categories. The first one is the light lepton scenario. I mean that the leptons are lighter than the electroweak, and another one is a lighter electroweak scenario, where the electroweak are smaller, lighter than the leptons. So depending on these two, depending on the mass spectrum, this light lepton region is actually this parameter region is already almost excluded by multi-lepton channel, because the dominant production channel is electroweak in this diagram. Then the electroweak decay into the lepton by emitting the leptons. So multi-lepton channel can eliminate, can exclude this region already. And also the pair production of lepton can also exclude this parameter region. So most of the parameter region are already excluded in this light lepton region. On the other hand, in the light electroweak region, instead of making this multi-leptons, the electroweak decay into the standard model boson, emitting decay into the neutralino with emitting the standard model boson. So the channel, the LHC channel, the standard model production plus missing transverse energy. And as you can see, even after the LHC run 2, almost all parameter regions are still allowed. So why is this boundary so weak? The reason is very simple. So I haven't explained, but we assume that the Wien mass is half of the Wien mass in this plot. Then in this is a plot of the ATLAS sensitivity. ATLAS exclusion. So this parameter region corresponds to here in this plot. And so such a parameter, such a mass region, it seems to be excluded by the WZ final state channel. However, we can easily see that the branching ratio of the next lightest neutrino decay into lightest neutrino plus Z is not unity, is not one in realistic setup. Actually, in this setup, they assume, the experimentalists assume that the branching ratio is over the one, is equal to one, but this is not realistic because in SUSY model, the V Z interaction does not exist. So the dominant channel is extracting neutrino decay into neutrino, lightest neutrino plus Higgs boson. So we need higher sensitivity on this channel, the production of WH plus large transverse energy. So this is an important target of the high luminosity LHC. And actually, how many minutes do I have? Okay. So
about 10 minutes.
Okay. So let me explain the Piabino scenario. So this is, I'm explaining the Piabino scenario because this is very special. So why this is special? In this case, the Bino and the left-handed SMU and right-handed SMUs are assumed to be right. Then the chirality flip of the left and chirality flip of the SMU is given by the tangent beta and also mu parameter. Actually, this vertex is proportional to mu times tangent beta. So we can consider the enhancement both by mu and tangent beta because there are no Higgs-no in the loop. This is different from the other two contributions because this contribution includes the Higgs-no. So that's why we cannot consider the large mu. But in this case, we can consider the large mu parameter regions. Actually, we consider that mu is maximized under several constraints, such as the vacuum stability constraint, or the experimental constraint, of course. And we found that the tangent, this is a plot of the tangent beta. So, okay, so I have to explain. This is a beam mass, and this is a SMU mass, like a SMU mass. And this is a plot of a tangent beta equal 50. And this yellow region is a mu g minus 2 parameter region. So as you can see, when we consider tangent beta 50, the allowed parameter region is really tiny. But if we consider tangent beta 5, the allowed parameter region is magnified. Actually, this is because when we consider larger tangent beta, then we don't have to consider large mu. Rather, the mu is expected to be small. Then such a small with large tangent beta enhance right Bino Higgs-no contribution here. And in this case, we can find that this right Bino Higgs-no contribution destructively interfere with the pure Bino contribution. So this is the reason why when we consider tangent beta 50, the allowed parameter region is very small. So smaller tangent beta is favored in this case. But of course, the mass region is really low. It's as large as 100 to 300 GB. So there are severe constraints come from the experiment LHC. Actually, the pair production of the Muon gives a tight constraint, but still there is a parameter region in between these constraints. Yeah, of course, this is very narrow. So you may consider that this is unnatural, but from the viewpoint of the dark matter, it's such a parameter is interesting. Actually, the dark matter is one of the big motivation of the supersymmetry. Oh, sorry. Okay, so the one of the famous scenario to explain the dark matter radical abundance is a thermal production. So, and the Bino is a well-known WIMP dark matter candidate. And as you know, the thermal radical abundance is proportional to the inverse of the annihilation cross-section. And the PRB when we consider the PRB dark matter, the dark matter abundance becomes much, much larger than the observed dark matter abundance. So we have to consider the mechanism to reduce the dark matter abundance. I mean, that's in order to, so we have to enhance the annihilation cross-section. So the Stark annihilation is one of the famous scenario. In this scenario, the star mass is very close to the Bino mass. I mean, that the degeneracy is favored in this scenario. So in this pure Bino scenario, this Stark annihilation happens naturally. So in this plot, mu is determined by reproducing the dark matter radical abundance. So this parameter region is allowed. So in this parameter region, mu g minus the anomaly is explained, and also dark matter radical abundance is explained. So this seems natural. And another important point of this result is that the wide parameter region can be tested by using a dark matter direct detection. So for instance, in the near future, xenon N-tons will start and Panda X also start. And these experiments can test the many of the wide of this parameter region. So we can test. Okay, so this is a summary. So the Fermilab confirms the Muon G minus result that, and now the deviation is 4.2 sigma level. And the white paper has been published, but non-issue on hadronic vacuum polarization was raised by the recent BMW result. And this tension has not been solved yet, unfortunately. But white beta is good. And the many new physics model has been proposed, include the SUSY. And SUSY is a major target. This is one of the major target of the Muon G minus 2 anomaly. And we show that today we show that such a parameter, such a scenario can be tested in the near future. Okay, thank you very much.
Thank you very much for a very nice talk. There was a question in the chat box. So Rohini, you can ask your question.
Okay, thank you. So Endo-san, thank you very much for a very nice and clear talk. I had two questions actually.
Yep.
The first one is about this electroweak precision testing, is constraints, electroweak precision constraints, or the analysis. Yeah, here.
Yep.
So the question I have is, can you tell us what kind of enhancement is required in the region less than 1 GeV to get agreement with the G-2? Meaning you said enhancement in region less than 1 GeV is allowed. But
Okay.
How much is that enhancement? Do you have a qualitative number for this? 1%, 2%?
Okay. Yep. Yeah, that's important. So this is a plot of the requirement of the enhancement.
Mm-hmm.
It's not easy to understand, unfortunately. So this is a percentage of the enhancement.
Okay.
And so this is the size of enhancement to explain the BNL. as a Fermi-level result. And this is the size of enhancement to explain the BMW result. And this is the experimental precision of the, I mean, the hadronic, the R ratio precision is here.
So it's by factors. I mean, okay.
Yeah.
It needs to be off by a few factor, at least a factor of 4.
At least after 4 years.
Okay,
and
so that's a big change. Okay.
Yeah.
All right.
So it must be tested in the near future.
I understand. I mean, it is not a minor thing. It's a huge.
Yeah, it's huge, quite huge.
Okay. Okay. No, thanks for this answer. And the second one, my question, I started thinking of the question when you were showing your G-2, the 3 supersymmetric contributions. Can you go to that slide?
Sure.
Yeah. So actually, I had the question when you were talking of light Vino Higgsino contributions. And somewhere I think you said that the Bino would be perhaps. Can you go to the slide where you discuss this light Vino Higgsino? Yeah. So here, when you say Bino LSP,
yes.
I was just wondering, again, the same thing which you so nicely explained later on for pure Bino, is that what is the mass of the left-handed muon here, and how do you adjust the relic, even if Bino is the LSP? Is the mass still very small to give you the co-annihilation? I mean, I was just not clear on that issue.
You mean that dark matter?
Yeah, the dark matter. So if Bino is the LSP,
yes.
How do you get the right dark matter? You get it by the light again with the left-handed muon, the relic, correct? Only with the left-handed muon which is being light.
Okay, so when the Bino is assumed to be lightest SUSY particle in this scenario, then only this tiny parameter region.
Then it's okay.
Yeah,
then it's okay.
Yeah,
then
it's consistent with the dark matter.
No. But then it's okay.
Yeah, if we forget about this condition, I mean, that's if we know either we know Higgsino, neutrino we know Higgsino is a LSP, then the situation changes drastically.
I can understand that.
Yep.
The minute you get some mixture, you can manage it.
Yep.
Okay. No, thank you very much for both the answers.
Thank you.
Thanks again.
Okay, so we can take a quick question. If there is, let us thank Dr. Endo. And thank you very much for your talk, Endo-san. So,
yep.